It would take a supercomputer thousands of years to work out P and Q by trial and error, making RSA and similar protocols practically unbreakable. Public key encryption scrambles data with an encryption key available to anyone. The data can only be unscrambled with a private key, known only to its owner. This method is effective for small amounts of data, but is too time-consuming for large amounts. The RSA algorithm and other public key encryption systems require a large collection of primes to act as P and Q. If the system relies heavily on too few primes, then it is possible for attackers to figure out some of the values for P and Q being used in everyday encryption. The solution is to have a supply of fresh primes. These are found by generating random numbers and testing their primality with Pierre de Fermat's little theorem. If a number is prime, when another number is raised to the power of p, and n is subtracted from the result, the answer is a multiple of p. Computers are not easily programmed to create truly random sequences of numbers, so companies use physical phenomena to generate them. Computers are programmed to follow the movements of lava lamps, measure radioactive decay, or listen to white noise made by radio transmissions, turning that input into random numbers to use for encryption. See also, group theory, the Riemann hypothesis, the Turing machine information theory proving Fermat's last theorem. In context. Key figure. Daniel Gorenstein field number theory before. 1832 Évariste Galois defines the concept of a simple group. 1869-89 Camille Jordan, a French mathematician, and Otto Holder, a German, prove that all finite groups can be built from finite simple groups. 1976 Croatian mathematician Swanimir Janko introduces the sporadic simple group Janko group 4, the last finite simple group to be discovered. After 2004 American mathematicians Michael Ashbacher and Stephen D. Smith complete the classification of finite simple groups begun by Daniel Gorenstein. Simple groups have been described as algebra's atoms. The Jordan-Holder theorem, proven around 1889, asserts that, just as all positive integers can be constructed from prime numbers, so all finite groups can be built from finite simple groups. In mathematics, a group is not simply a collection of things, but a specification of how the group members can be used to generate more members, for example, by multiplication, subtraction, or addition. In the early 1960s, American mathematician Daniel Gorenstein began to pioneer the classification of groups and issued his complete classification of finite simple groups in 1979. There are similarities between simple groups and symmetry in geometry. Just as a cube rotated through 90 degrees looks the same as it did before it was rotated, the transformations associated with a regular 2D or 3D shape can be arranged into a type of simple group known as a symmetry group. Infinite and finite groups. Some groups are infinite, as in the group of all integers under addition, which is infinite because numbers can be added infinitely. However, the numbers 1, 0, and 1 with the multiplication operation form a finite group. Multiplying any members of the group produces only 1, 0, or 1. All the members of a group and the rules for generating it can be visualized using a Cayley graph. A group is simple if it cannot be broken down into smaller groups. While the number of simple groups is infinite, the number of types of simple group is not, at least, not when simple groups of finite size are considered. In 1963, American mathematician John G. Thompson proved that, with the exception of trivial groups, for example, 0 plus 0 is equal to 0, or 1 1 equals 1, all simple groups have an even number of elements. This led Daniel Gorenstein to propose a more difficult task, the classification of every finite simple group. This Cayley graph shows all 60 elements of the group A5, and how they relate to each other. Since A5 has a finite number of elements, it is a finite group. A5 is also a simple group. It has two generators. The monster. There are precise descriptions of 18 families of finite simple groups, with each family related to symmetries of certain types of geometrical structure. There are also 26 individual groups called sporadic groups, the largest of which is called the monster, which has 196,883 dimensions and approximately 8,1053 elements. Every finite simple group either belongs to one of the 18 families or is one of the 26 sporadic groups. Daniel Gorenstein. Born in Boston, Massachusetts, in 1923, Daniel Gorenstein had taught himself calculus by the age of 12 and later attended Harvard University. There, he became acquainted with finite groups, which would become his life's work. After graduating in 1943, he stayed at Harvard for several years, first to teach mathematics to military personnel during World War II, then to earn his Ph.D. under mathematician Oscar Zariski. In 1960-61, Gorenstein attended a 9-month program in group theory at the University of Chicago, which inspired him to propose a classification of finite simple groups. He continued to work on this project until his death in 1992. Key works: 1968 Finite Groups. 1979 The Classification of Finite Simple Groups, 1982 Finite Simple Groups. 1986 Classifying the Finite Simple Groups. See also, the Platonic Solids Algebra Projective Geometry Group Theory Cryptography Proving Fermat's Last Theorem. In context. Key figure: Andrew Wiles Field Number Theory before 1637 Pierre de Fermat states that there are no sets of positive whole numbers x, y, and z that satisfy the equation x plus y equals z, where n is greater than 2. However, he does not provide the proof. 1770 Swiss mathematician Leonhard Euler shows that Fermat's last theorem is true when n equals 3. 1955 in Japan, Yutaka Taniyama and Goro Shimura proposed that every elliptic curve has a modular form. After 2001 the Taniyama-Shimura conjecture is established. It becomes known as the modularity theorem. When he died in 1665, French mathematician Pierre de Fermat left behind a well-thumbed copy of Arithmetica by the 3rd century CE Greek mathematician Diophantus, its margins marked with Fermat's ideas. All the questions posed in Fermat's marginal scribbles were later solved, except for one. He left a tantalizing note in the margin: "I have discovered a truly marvelous proof, which this margin is too small to contain here." Fermat's note related to Diophantus's discussion of Pythagoras's theorem, that in a right-angled triangle the square of the hypotenuse is equal to the sum of the squares on the other two sides, or x plus y equals z. Fermat knew that this equation had an infinity of integer solutions for x, y, and z, such as 3, 4, and 5, 12, and 13, known as Pythagorean triples. He then wondered if other triples could be found to the power of 3, 4, or any integer beyond 2. The conclusion Fermat reached was that no integer greater than 2 could stand for n. Fermat wrote, "It is impossible for a cube to be the sum of 2 cubes, a fourth power to be the sum of 2 fourth powers, or in general for any number that is a power greater than the second to be the sum of 2 like powers." Fermat never revealed the proof he claimed to have for his theory, and so it remained unsolved, becoming known as Fermat's last theorem. Many mathematicians attempted to reconstruct Fermat's claimed proof after his death, or to find their own. But despite the seeming simplicity of the problem, no one was successful, although a century later Leonhard Euler did prove the theory where n equals 3. Finding a solution. Fermat's last theorem remained one of the great unsolved problems in mathematics for more than 300 years, until it was proved by British mathematician Andrew Wiles in 1994. Wiles had first read about Fermat's challenge when he was 10. He had been amazed that he, just a boy, could make sense of it, and yet the best mathematical minds in the world had failed to prove it. It made him want to study mathematics at the University of Oxford, and then to get his Ph.D. at Cambridge. There, he chose elliptic curves as the area of study for his doctoral thesis, a subject that seemed to have little to do with his interest in Fermat. Yet it was this branch of mathematics that would enable Wiles to prove Fermat's last theorem. In the mid-1950s, Japanese mathematicians Yutaka Taniyama and Goro Shimura had made the bold step of linking two apparently unrelated branches of mathematics. They claimed that every elliptic curve could be associated with a unique modular form, one of a class of highly symmetrical structures belonging to number theory. The potential importance of their conjecture was gradually understood over the next 3 decades, and it became part of an ongoing program to link different mathematical disciplines. However, no one had any idea how to prove it. In 1985, German mathematician Gerhard Frey made a link between the conjecture and Fermat's last theorem. Working from a hypothetical solution to the Fermat equation, he constructed a curious elliptic curve that appeared not to be modular. He argued that such a curve could only exist if the Taniyama-Shimura conjecture were false, in which case Fermat's last theorem would also be false. On the other hand, if the Taniyama-Shimura conjecture were true, Fermat's last theorem would follow. In 1986, Ken Ribot, a professor at Princeton University, in New Jersey, managed to prove Frey's conjectured link. Wiles's investigation of Fermat's last theorem began with his study of elliptic curves, which are described by the equation y equals x plus b, where a and b are constants. Proving the unprovable. Ribot's proof electrified Wiles. Here was the chance he had been waiting for. If he could prove the seemingly impossible Taniyama-Shimura conjecture, then he would also prove Fermat's last theorem. Unlike most mathematicians, who like to work collaboratively, Wiles decided to pursue this goal on his own, telling no one except his wife. He felt that to talk openly about working on Fermat would stir up excitement in the mathematics community, and perhaps lead to unwanted competition. However, as the proof reached its final stages, in the 7th year of working on it, Wiles realized he needed help. At the time, Wiles was employed at the Institute for Advanced Study in Princeton, home to some of the world's finest mathematicians. These colleagues were completely astounded when Wiles revealed that he had been working on Fermat while still carrying out his daily tasks of lecturing, writing, and teaching. Wiles recruited the help of these colleagues for the final step in compiling his proof. He turned to American mathematician Nick Katz to check his reasonings. Katz could find no errors, so Wiles decided to go public. In June 1993, at a conference at the University of Cambridge, Wiles delivered his results. Tension rose as he piled his results one on top of the other, with only one end in view. He delivered his final line, which proves Fermat's last theorem, smiled, and added, "I think I'll leave it there." Some mathematics problems look simple. There's no reason why these problems shouldn't be easy, and yet they turn out to be extremely intricate. Andrew Wiles. Fixing an error. The next day, the world's press was full of the story, transforming Wiles into the world's most famous mathematician. Everyone wanted to know how this problem had finally been solved. Wiles was delighted, but then came a twist. There was a problem with his proof. The results had to be verified before they could be published, and Wiles's proof covered scores of pages. Among the reviewers was Wiles's friend Nick Katz. For a whole summer Katz went through the proof line by line, querying and questioning until the meaning was clear. One day, he thought he had spotted a hole in the argument. He emailed Wiles, who replied, but not to Katz's satisfaction. More emails followed, before the truth emerged. Katz had found a flaw at the heart of Wiles's work. A vital point in the proof contained an error that undermined Wiles's method. Suddenly Wiles's approach was brought into question. Had he worked with others rather than alone, the error might have been identified earlier. The world believed that Wiles had resolved Fermat's last theorem, and it was waiting for the finished, published proof. Wiles was under immense pressure. His mathematical achievements so far had been impressive, but his reputation was at stake. Day after day, Wiles tried different approaches to the problem, which proved futile. As his fellow IAS mathematician Peter Sarnak said, it was like pinning down a carpet in one corner of a room, only for the carpet to pop up in another. Eventually, Wiles turned to a friend, British algebra specialist Richard Taylor, and they worked together on the proof for the next 9 months. Wiles was close to having to admit that he had claimed a proof prematurely. Then, in September 1994, he had a revelation. If he took his present problem-solving method and added its strengths to an earlier approach of his, then one might fix the other, allowing him to solve the problem. It seemed a small insight, but it made all the difference. Within weeks, Wiles and Taylor had plugged the gap in the proof. Nick Katz and the wider mathematical community were now convinced there were no mistakes, and Wiles emerged for a second time as the conqueror of Fermat's last theorem, this time on solid ground. I had this rare privilege of being able to pursue in my adult life what had been my childhood dream. Andrew Wiles. After the theorem. Fermat was amazingly far-sighted in his original conjecture, but it is unlikely that the marvelous proof he claimed to have discovered existed. The idea that every mathematician since the 1600s could have missed a proof that a mathematician from Fermat's time could have discovered is inconceivable. In addition, Wiles solved the theorem using advanced mathematical tools and ideas invented long after Fermat. In many ways, it is not the proving of Fermat's last theorem that has significance, but rather the proofs used by Wiles. A seemingly impossible problem about integers had been solved by marrying number theory to algebraic geometry, using new and existing techniques. This in turn opened up new ways of looking at how to prove many other mathematical conjectures. Andrew Wiles. The son of an Anglican priest who later became a professor of divinity, Wiles was born in Cambridge in 1953, and was a passionate problem solver in mathematics from an early age. Awarded his first degree in mathematics at Merton College, Oxford, and his doctorate at Clare College, Cambridge, he took up a post at the Institute for Advanced Study in Princeton in 1981, and was appointed professor there the following year. While in the U.S., Wiles made contributions to some of the most elusive problems in his field, including the Taniyama-Shimura conjecture. He also began his long solo attempt to prove Fermat's last theorem. His eventual success led to him receiving the Abel Prize, the highest honor in mathematics, in 2016. Wiles has also taught in Bonn and Paris, and at the University of Oxford, where he was appointed Regius Professor of Mathematics in 2018. A new mathematics building at Oxford, as well as an asteroid, 9999 Wiles, have been named after him. See also, Pythagoras-Diophantine equations, probability elliptic functions, Catalan's conjecture, 23 problems for the 20th century finite simple groups. In context. Key figure. Grigori Perelman fields. Geometry, topology before. 1904 Henri Poincaré states his conjecture on the equivalence of shapes in 4D space. 1934 British mathematician Henry Whitehead stirs interest in Poincaré's conjecture by publishing an erroneous proof. 1960 American mathematician Stephen Smale proves the conjecture is true in the fifth and higher dimensions. 1982 Poincaré's conjecture is proved in 4 dimensions by American mathematician Michael Friedman. After 2010, when Perelman rejects the Clay Millennium Prize, the £1 million award is used to set up the Poincaré Chair for gifted young mathematicians. In 2000, the Clay Mathematics Institute in the U.S. celebrated the millennium with 7 prize problems. Among them was the Poincaré conjecture, which had challenged mathematicians for nearly a century. Within a few years, it was solved by a little-known Russian mathematician, Grigori Perelman. Poincaré's conjecture, conceived by the French mathematician in 1904, is stated as, every simply connected, closed 3-manifold is homeomorphic to the 3-sphere. In topology, a field that studies the geometrical properties, structure, and spatial relations of shapes, a sphere. is said to be a two-manifold with a 2D surface existing within a 3D space, a solid ball, for example. A three-manifold, such as the three-sphere, is a purely theoretical concept. It has a 3D surface and exists in a 4D space. The description, simply connected, means that the figure has no holes, unlike a bagel or hoop shape, and closed means the shape is limited by boundaries, unlike the open endlessness of an infinite plane. In topology, two figures are homeomorphic if they can be distorted or stretched into the same shape. While the question of whether every closed three-manifold could be deformed to take the shape of a three-sphere is hypothetical, Perelman has claimed that it holds the key to understanding the shape of the universe. Finding a solid proof. Initially, it proved easier to substantiate the conjecture for manifolds of the fourth, fifth, and higher dimensions than it was for three manifolds. In 1982, American mathematician Richard Hamilton attempted to prove the conjecture using Ricci flow, a mathematical process that potentially allows any 4D shape to be distorted to an increasingly smooth version, and ultimately to a three-sphere. However, the flow failed to handle spike-like singularities, deformities including cigars, and infinitely dense necks. Perelman, who learned much from Hamilton during a 2-year fellowship at Berkeley in the early 1990s, continued to study Ricci flow and its application to the Poincare conjecture when he returned to Russia. He masterfully overcame the limitations that Hamilton encountered by using a technique called surgery, in effect cutting out the singularities, and was able to prove the conjecture. A three-sphere is the 3D equivalent of a spherical surface, that is a two-dimensional surface, or two-sphere, such as the ball shown here. To appreciate the shape of the ball, it has to be viewed in 3D space. To see a three-sphere requires 4D space. Surprising the math world. Perelman had achieved success quietly. Unconventionally, he posted his first 39-page paper on the subject online in 2002, emailing a summary to 12 mathematicians in the US. He published 2 more installments a year later. Others reconstructed his results and explained them in the Asian Journal of Mathematics. Finally, his proof was fully accepted by the mathematical community in 2006. Since then, Perelman's work has been closely studied, fueling new developments in topology, including a more powerful version of his and Hamilton's technique for using Ricci flow to smooth singularities. Perelman's proof solved a problem that for more than a century was an indigestible seed at the core of topology. Dana Mackenzie, American science writer. Grigori Perelman. Born in 1966 in St. Petersburg, Grigori Perelman developed a passion for mathematics from his mother, who taught the subject. Aged 16, he won a gold medal at the International Mathematical Olympiad in Budapest, achieving a perfect score. A successful academic career followed, including a spell at several research institutes in the US, where he solved a major geometry problem called the Soule conjecture. While there, he met Richard Hamilton, whose work influenced his proof of the Poincare conjecture. The reclusive Perelman did not enjoy the fame his proof brought him. He turned down the 2 greatest accolades for a mathematician, the Fields Medal in 2006 and the Clay Mathematics Institute Prize in 2010, saying it belonged as much to Hamilton. Key works. 2002, The Entropy Formula for the Ricci Flow and its Geometric Applications. 2003, Finite Extinction Time for the Solutions to the Ricci Flow on Certain 3 Manifolds. See also, The Platonic Solids Graph Theory Topology Minkowski Space Fractals.